Hi everyone, I hope you're okay, and I hope that the videos will keep uploading and helping you out. On this video, guys, it's a continuation from the application of Coulomb's law. Right, together. Yes. On the previous video, we were only focusing on two charges, but now we'll focus on three charges and learn how to calculate the net electrostatic force if you are given three charges. Are you together? And on the last question, we will learn how to calculate the magnitude of a charge if ever we are given the net electrostatic force. Okay, we are told that three charged spheres, A of magnitude -2 microcoulombs, B of magnitude -3 microcoulombs, and C of magnitude +2 microcoulombs. And then we are told that B is in the middle of the two charges. A is 0.5 meters to the left of B, while C is 0.75 meters to the right of B. All right, together. And then on the first question, guys, they just want us to calculate the net electrostatic force experienced by charge A. The first thing you need to do, guys, is to draw your free body diagram. All right, together, and check how does charge A behave as a result of the other two charges. All right, together. So this free body over here will represent charge A. Firstly, I want to know how is charge A going to behave as a result of charge B. Are we together? Both of the two charges have the same polarity. They are both negative. Are we together? And hence there is a repulsive force between them, which basically means they will just push one another away. So charge B will push charge A towards the left. This is the force, this is the electrostatic force that exists between charges A and B. Are you together? And then now I need to check the behavior of charge A as a result of charge C. Both charges have different polarity. The other one is positive and the other one is negative, which simply means there's an attraction force between these 2 point charges. Are you together? But remember that, guys, my reference is charge A. I'm only focusing on the behavior of charge A. Né? So charge C will try to pull charge A towards the right because charge A will be attracted to charge C. Are you together? Remember that, guys, force is a vector quantity, so it's quite important for a force to have it's quite important for you to choose a positive direction. Are you together? So if I choose the right hand side movement as positive, I will do so for all the questions because I will calculate the net force exerted on B and on C. Né? And for all these questions, guys, I want to choose the right hand side as positive. You can choose left as positive. There's no problem as well. Né? Okay, so for me to find the resultant force, I'll simply say fNet is basically equals to the electrostatic force between charges A and C minus the electrostatic force between charges A and B. I'm subtracting the one of A and B. Why? Because it's moving in the opposite direction. Okay, that's K QA QC over R squared minus K QA QB over R squared. Remember that, guys, K is just a constant. It's a Coulomb's constant. It's given at the back of your question paper. That's 9 times 10 to the power 9. The charge on A is -2 microcoulombs. But remember that whenever we substitute, if we're calculating the electrostatic force, we don't have to substitute the signs. Né? So I'll just put 2 times 10 to the power -6, and the charge of C is also 2 microcoulombs. That's 2 times 10 to the power -6 all over R squared. The distance between charges A and C is just 0.5 plus 0.75, and we will get 0.5 plus 0.75 is just 1.25 meters. Then it's all squared, right? Okay, and then for the electrostatic force between A and B, we'll still substitute the constant. That's 9 times 10 to the power 9. The charge on A That's 2 times 10 to the negative 6. The charge on B, it's 3 times 10 to the negative 6. The distance between both A and B is just 0.5. So that's 0.5 squared. So all you have to do, guys, is to just punch this on your precious calculator for you to get the answer. 9 times 10 to the power 9, 2 times 10 to the power negative 6, times 2 times 10 to the power negative 6 again, all over 1.25 squared minus 9 times 10 to the power 9, 2 times 10 to the power negative 6, and 3 times 10 to the power negative 6, all divided by 0.5 squared. And this will give me a negative 1.93 times 10 to the power negative 1 coulomb. Are you together? Since this is negative, guys, it simply means that my fNet is towards the left or the western direction. So the final answer should say fNet is equals to 1.93 times 10 to the power negative 1 newtons to the left. That's how, guys, you calculate fNet, né? Okay, now let's go ahead and calculate the net electrostatic force experienced by a charge B. Let's use a different color. This will represent to B, né? Okay, let's check the force that exists between A and B. Remember that, guys, my reference is charge B, né? I will focus on how does charge B behave as a result of the other two charges. Between charges A and B, we have a repulsive force. Why? Because both of the charges are negative. So basically, charge B will be pushed away by charge A. This is the electrostatic force that exists between charges A and B. Are you together? Now let me check the behavior of B as a result of charge C. Né? B and C have different polarity. Are you together? So these two charges will attract one another, but I'm only focusing on charge B. Are you together? So charge B will be attracted to C, which simply means charge B will be moving towards charge C. So this is the force between charge B and charge C. Both of my forces are in the same direction. Remember that I've already chosen the right hand side as positive. So for me to calculate, I'll simply say fNet is basically the electrostatic force between charges A and B plus the electrostatic force between charges B and C. That's K QA QB over R squared plus K QB and C over R squared. Then all you have to do, guys, is to just substitute. Né? The magnitude of K is just 9 times 10 to the power 9. 2 times 10 to the power negative 6, the charge on A, né? And the charge on B is just 3 times 10 to the negative 6. The distance between A and B, remember that, guys, it is 0.5, right? That's 0.5 squared plus 9 times 10 to the power 9. The charge on B, that's 3 times 10 to the power negative 6. And the charge on C, that's 2 times 10 to the power negative 6, all over, that's 0.75 squared. And then I'll simply find my resultant force. 9 times 10 to the power 9, 2 times 10 to the power negative 6, multiplied by 3 times 10 to the power negative 6, all over 0.5 squared, plus 9 times 10 to the power 9, 3 times 10 to the power negative 6 and 2 times 10 to the power negative 6, and our denominator is just 0.75 squared. So our final answer, guys, is just 3.12 times 10 to the negative 1 newtons. Since we have a positive answer, it simply means that our fNet is towards the right hand side. fNet is towards the right hand side. Ne? Okay, now let's go and calculate the net electrostatic force experienced by our charge C. Ne? Firstly, I must draw my free body diagram. Ne? I want to see how is charge C going to behave as a result of both A and B. Firstly, between B and C, B is positive while, C is positive while B is negative, right? So there will be an attraction force. All right, together, there will be an attraction force. So C will be pulled towards the left by charge B. So this over here will be the force that exists between charges B and C. Okay, now let's go and check how is C going to behave as a result of A. B and A have different polarity. One charge is positive and the other is negative. So they will be so they will be attracted to one another, such that charge C will be pulled by charge A towards the left. So this over here represents the force that exists between charges A and C. So both of the forces are towards the left. So I'm expecting to find the resultant force, my net resultant force, to be on the left hand side direction. So fNet is basically equals to negative FAC minus, plus a negative. Remember that, guys, I've chosen my right hand side to be positive for all these forces, ne? And I was not forced. It was just my choice. Right, together. So every force which goes to the right is positive, and to the left will be negative, ne? Okay, so this will simply give me negative K QA QC over R squared minus K QB QC over R squared. Ne? This is negative 9 times 10 to the power 9. The charge on A is just 2 times 10 to the negative 6. The charge on C, that's 2 times 10 to the negative 6. The distance between A and C, let me confirm, that's 1.25. Ne? It's 0.5 plus 0.75. We'll end up getting 1.25 squared minus 9 times 10 to the power 9. The charge on B is 3 times 10 to the power negative 6. And then the charge on C is just 2 times 10 to the power negative 6. The distance between B and C is just 0.75. So this will give me the resultant force. That's negative 9 times 10 to the power 9, 2 times 10 to the power negative 6, and another 2 times 10 to the power negative 6, all over 1.25 squared minus, I have 9 times 10 to the power 9, 3 times 10 to the power negative 6, and 2 times 10 to the power negative 6, all over 0.75 squared. What's wrong now? Let me just, excuse me about that, 0.75 squared. Oh, I'm struggling to press my calculator correctly. What's going on? Oh. So this will give me negative 1.19 times 10 to the power negative 1 newtons. So therefore the resultant force is basically 1.19 times 10 to the power negative 1 newtons to the left. That's how, guys, we deal with finding the resultant force if you have three charges. Né? Okay, let's do the last question. We are told that 3-point charges P, Q, and R are placed next to one another. The charge on P is 1.5, is a positive 1.5 nanocoulombs. That's positive 1.5 nanocoulombs. The charge on Q is just negative 2 nanocoulombs. And then R is just an unknown positive charge. Okay, I know that R is just a positive charge. If R experiences a net force of 1.27 micronewtons to the left, calculate the charge on R. Firstly, we must draw our free body diagram. Né? This free body will represent the behavior of charge R as a result of both charges P and Q all together. Okay, for charge R, né? Between charges R and Q, I have an attraction force. Why? Because Q is negative and R is positive. So R will be pulled by charge Q towards the left. This will be the force that exists between charges Q and R. Are you together? And then now I want to see how is R going to behave as a result of P. Both of the two charges are positive, so basically they will just repel one another. They'll just push one another away. So charge R will be pushed by charge P towards the right. So this is the force between charges P and R. Remember that, guys, I've previously chosen my right hand side to be positive, né? And I still stick by that. It's my choice. I'm not forced. Are you together? So for me to calculate fNet, I'll simply say fNet is basically equals to the force that exists between charges P and R minus the one that exists between charges Q and R. Are you together? And then I still have fNet is equals to K QP QR all over R squared minus K QQ and QR over R squared. Now all I have to do is to just substitute. Né? I am given the magnitude and direction of my fNet. So that's 1.27 times 10 to the power negative 6. But remember that, guys, I have chosen the right hand side to be positive, né? But my fNet is towards the left, so it has to be negative. Are you together? And then I have 9 times 10 to the power 9 multiplied by the charge on P. That's 1.5 times 10 to the power negative 9 multiplied by the charge on R. Remember that, guys, you are looking for the magnitude of the charge on R, né? The distance between P and R, that's 0.1 plus 0.2. So the distance is basically 0.3. This is minus 9 times 10 to the power 9. Excuse me. The magnitude of charge Q is just 2 nanocoulombs multiplied by QR all over. The distance between Q and R is just 0.2. Okay, and then I still have negative 1.27 times 10 to the power negative 6. What's going on now? Why is this thing not writing? Excuse me about that, guys. I hope in the meantime you're subscribing, né? Okay. I have negative 1.27 times 10 to the power negative 6. Please punch all of this, guys, to your calculator. Punch all of that. You'll simply have 9 times 10 to the power 9, and then 1.5 times 10 to the power negative 9, all over 0.3 squared. So this will just give us 1.5 times 10 to the power 2 multiplied by QR, ne? Minus, do the same thing over there. We have 9 times 10 to the power 9 multiplied by 2 times 10 to the power negative 9, all over 0.2 squared. So that will give us 4.5 times 10 to the power 2 multiplied by QR. Are we together? Okay, and then how can we find this? We still have negative 1.27 times 10 to the power negative 6. Okay, I can take out a common factor over there. QR is my common factor. I will be left with 1.5 times 10 to the power 2 minus 4.5 times 10 to the power 2. Ne? QR is my common factor. I'll just divide both sides by 1.5 times 10 to the power 2 minus 4.5 times 10 to the power 2 on both sides. So that's how I'll be left with QR. This will cancel that, and therefore QR is just negative 1.27 times 10 to the power negative 6 all over 1.5 times 10 to the power 2 minus 4.5 times 10 to the power 2. I didn't insert the other brackets. So the magnitude, guys, on charge R is just 4.23 times 10 to the power negative 9 coulombs. That's how, guys, we use that's how we use our resultant force to calculate the charge. Firstly, draw a free body diagram showing the electrostatic force that exists, and then the rest is history, guys. Ne? Just stay tuned, guys. On the next video, I'll be posting the same thing, calculating resultant force, but now it will be on different dimensions. You'll have charges like this, ne? Calculating the resultant force on that charge there. But yeah, just stay tuned, guys, and make sure that you do subscribe, you like the videos, do share the video as well to your peers, please. Bye.